Good day, everyone. Yesterday, I published a video on YouTube here where I showed my intention in teaching finite element method in solving structural engineering problems. I also gave a brief introduction of the theories of one-dimensional finite element procedure in that video. In today's video, I'm going to analyze a one-dimensional problem by using finite element procedure and also by using hand calculation. The problem depicted on this slide includes a two material parts. Material part 1 denoted by this triangle 1 and material part 2. And there is also a 160 kilonewton tension force at node 1 and node 3, which apply tension force on the body. The geometric and the material property of each material part is given by A1, E1 and A2, E2, where A is the cross-sectional area of each material part and E is the Young modulus. And in this problem, the unit for E is in gigapascal. It is required to determine the deformation at node 1, at node 2, and node 3 by using two linear finite elements. And it's also required to determine the stresses in each of the material parts, material part 1 and material part 2. In addition to all this, I would like to say that the finite element procedure is not a method that actually gives exact solution. The accuracy of the finite element solution most time depend on the number of finite elements in which you break your structural problem into. But in this problem, using a two finite element is enough and very appropriate and actually give accurate results. It actually gives the exact solution when compared to the hand calculation. But in many other finite element problem, you might need to use smaller finite elements to get more accurate results. To solve this problem using the finite element procedure, as I briefly explained in my previous video, I said we need to impose boundary condition on the problem. As the problem is right now, we cannot use a finite element procedure to solve the problem because the problem does not have a boundary condition. So I'll move to the next slide. Since the structural problem that we're given does not have a boundary condition, and we want to use a finite element procedure to solve this problem, we can make an assumption that at node 1, at this point here, at node 1, we have a pin support. It's actually, I actually drew the diagram here. At node 1, we have a pin support. And if we apply a 160 kilonewton point load at node 3, we are going to have the same response in the structural body for a problem with 160 kilonewton applied at both node 1 and node 2. Sorry, at both node 3 and node 1. So applying a 160 kilonewton at node 1 and node 3 is equivalent to assuming a pin support at node 1 and applying a 160 kilonewton at node 3. So the finite element procedure can be easily applied to this problem because it has a boundary condition. So this is what we are going to use to analyze this problem. This is the finite structural model we are going to use to solve the problem. Again, in every finite element analysis, one of the first steps you must do, one of the initial procedure is to define the number of finite elements that you want to use in your analysis. In this problem, as instructed, we are asked to use two finite elements to solve the problem. I can decide to use more finite elements, but it does not matter. Two finite elements is just enough and appropriate to solve this problem. And using two finite elements actually gives the exact solution when compared with hand calculation. So there is no need to use more than two finite elements to solve this problem. In my next slide, I'm going to solve the original the original problem given to us by hand calculation. I'm going to solve this problem without boundary condition by hand calculation. And at the end of this video, we are going to compare the hand calculation results with our finite element solution. So I'm going to the next slide now. So this is the hand calculation using the original model given in the question. In solving this problem by hand calculation, the problem can be broken down into two parts, the material part 1 and material part 2. And the key to solving this problem by hand calculation is to realize that in both material, the area load is actually 160 kilonewton. That is actually the key to solving this problem. We can we can calculate the extension and the stresses in each element by using the stress strain relationship, the stress strain formula from Hooke's law. So that we can use the stress strain formula to actually determine the extension in each material part and the internal stress in each material part. So I say here, let dl1 and sigma 1 represent the extension and stress in element 1 respectively. And if we should do that, the extension in material 1 is given by, the extension formula is given by P, the force times the length over Young modulus times the area. That is the formula using stress strain relationship. And for material 1, the P, the force, is 160 kilonewton. My unit I'm using for my calculation for the force is in Newton. And my dimension for length is in millimeter. And my unit for area is in millimeter square. So for the P is 160 times 10 to 3 Newton. So that's why 160 times 1000 is written here, multiplied by the length of the material is 90 mm, that's why we have 90 mm, we have 90 here, divided by the Young modulus E, and I put this relationship here so that you understand the relationship between gigapascal, megapascal, and Newton per millimeter square. You should know that 1 megapascal is also equivalent to 1 Newton per millimeter square. And so you should also, the relationship that connects gigapascal, megapascal, and Newton per millimeter square is given here. Say we have 200 gigapascal. This 200 gigapascal is equals to 200 times 10 to the power 3 megapascal, which is also equivalent to 200 times 10 to the power 3 Newton per millimeter square. So the unit I want is Newton per millimeter square. So my E is equals to 200 times 10 to the power 3 Newton per millimeter square. So that is why I have 200 times 1000 here. And my cross-sectional area, A1, is given in the question as 50 mm square. So that's why 50 is here. So if we do this calculation, you get 1.44 mm. So this means that element 1 is stretched by 1.44 mm under 160 kilonewton tension force. Also, we can calculate the stress in material 1 using the stress strain relationship. Also, because we know that we know the axial force acting on the member is 160 kilonewton, we can actually say P over A equals to the stress. And we know the P is equals to 160 times 1000 Newton, and A is 50. So if we do this calculation, we get 3200 megapascal. But we apply this formula, stress equals to Young modulus times the strain. This small e means the strain, and the strain is equals to the change in length over the original length. The E is 200 times 1000. The change in length, which we have calculated here, that is the extension, is 1.44 mm. So that's why we have 1.44 here, divided by the original length, 90 mm. So if we do this calculation, you also get the same 3200 megapascal. So we can use either of the two formula. So the 160 kilonewton tension force stretches material 1 by 1.44 mm, and it induced an internal stress of 3200 megapascal. The same thing can be applied. What we did for material 1 can also be applied to material 2. So I'm not going to go into the same explanation. Under the 160 kilonewton force, material 2 is stretched by 0.96 mm, and the internal stress generated is 1600 megapascal. Now we are going to use MATLAB. We're going to use MATLAB to solve this same problem by applying the finite element procedure, the finite element approach. Problem will be solved in this video using the elimination method approach. The penalty method approach will be covered in my next lesson. Now we have moved to the MATLAB working environment. Before I start to explain the solution of this problem on MATLAB, I would like to inform you that all my MATLAB codes are written using the MATLAB live scripts. I do not use the command window, which is I do not use the command window in solving problem in MATLAB. I use the MATLAB live script, which is the interface above the command window here. I would like to give you an overview of how the MATLAB live scripts work before I start explaining the solution to our finite element problem. So to create a MATLAB live script, what you need to do, you need to go to the Home tab. To create a new MATLAB live script, you need to go to the Home tab. Under the File panel, panel, you click on New Live Scripts. So if you click on a new live script, a new live script file will be formed where you can write all your MATLAB code and you can run it and get a solution. So this is a new live script that MATLAB has opened for us. So here I can write my codes. Let me say A equals to say 45, B equals to A minus say 30. So I'm waiting my MATLAB code. Now to run this code, I'll come to the Live Editor tab and I'll click on Run. When I click on Run, MATLAB goes through my MATLAB code and it calculates the value of A and B is stored in the MATLAB memory. Apart from writing the MATLAB code, you can decide to write text in the MATLAB live script environment. To do this, under the text panel, you click on text. This text you are writing is a non-MATLAB code. and you normally want to say you want to explain how your code works, you can put a text, you can accompany your MATLAB code with a piece of text. Say I want to say solution to the problem, mistake, solution to the problem. You can write anything here, but these are just text. They are not MATLAB code. You can even copy images. You can copy and paste images in this MATLAB live script environment to better explain, say, your MATLAB algorithm, your MATLAB code, your MATLAB line of codes. So now I'm going to close this live script because I'm not actually going to use it. I have already written my MATLAB code for our one-dimensional problem, which I solve using the elimination method. So I am going to explain each line of code in this live script for solving our problem. This is actually an image which I copy and paste in this live script environment. So this is our finite structural model. The finite structural model has a pin support at node 1 and at node 3. We have a 160 kilonewton applied horizontal load. We have our geometric and material properties defined by A1, E1, and A2, E2. And the length of each part 1 and part 2, is 90 mm and 120 mm respectively. So the first step in solving this problem is for us to agree on the number of finite elements we use to solve this problem. The question actually instructed us to use two linear finite elements. We can decide to use more than two linear finite elements in which we'll also get the same results, but two finite elements is actually enough and appropriate to solve this particular type problem. So since we are using two finite elements, means that our finite structural model will have two parts. The part between node 1 and node 2 and the part between node 2 and node 3. So we have two linear finite elements denoted by the numbering in the green triangle, number 1 and number 2. Now we number our nodes. We number our nodes of our finite element model. So this number 1 here, this is node number 1, this is my node number 1, my node number 2, and my node number 3. So this finite element model has 3 nodes, and you will also need to define our degree of freedom. Since this is a one-dimensional problem, each node has 1 degree of freedom. So at node 1 we have Q1 degree of freedom. At node 2 we have Q2 degree of freedom. At node 3 we have Q3 degree of freedom. So after we have defined our element and our node and degree of freedom numbering, the next step is to define our material and geometric property of each element 1 and element 2. The first element in the question, it is we need to define the first element. For the first element, we need to define the Young modulus, the cross-sectional area, and the length of the element. The unit I'm using for my force is Newton. I'm repeating again. The unit I'm using for my force is Newton. The unit for length is in mm, and the unit for area is in millimeter square. So for the first element, it is given that the cross-sectional area is 50 mm square. The Young modulus is 200 kPa, and the length of element 1 is 90 mm. So E1, let E1 be my Young modulus for element 1, given as 200 times 10 power 3 Newton per millimeter square. L1 is the length of my element 1, 90 mm. A1 is the cross-sectional area, 50 mm square. Once I write this code and I click on run here, these values are stored in the MATLAB memory and are displayed under the MATLAB code. So here we see E1 equals to 200,000 Newton per meter square, L1 equals to 90, A1 equals to 50 mm square. So we do the same thing for the material 2, for the element 2. We define the material and the geometric property. So E2 is still the same 200,000 Newton per millimeter square. L2 is 120 mm, as stated in the question, 120 mm. A2 is 100 mm square, as stated in the question, 100 mm square. So we write the MATLAB code and we run. E2, L2, A2 gets stored in the MATLAB memory. So after we have defined the material and the geometric property, the next step is to calculate the local stiffness matrix of each element. So we start from element 1. We calculate the local stiffness matrix of each element using this formula, E A over L times this matrix. So we can define the local stiffness matrix of element 1 by using the geometric and material property which we have already stored in the MATLAB memory. So the E here will for K1. I'm representing my local stiffness matrix of element 1 by K1. So the E for K1 is E1, which I've stored in my MATLAB memory at the beginning. The A is A1, which is 50. The L is L1. The length is L1, which is 90 mm, multiplied by this matrix. This is how you denote the matrix in MATLAB. So once I've written this code and I click on run, K1 matrix gets calculated and also gets stored in the MATLAB memory. Now we have calculated our local stiffness matrix of element 1. We do the same thing for K2, exactly the same thing, but we use the material property of element 2, E2, A2, L2. So if we do that, we write the code, which is this. K2 represents the local stiffness matrix of element 2. So I'm defining K2 as my local stiffness matrix of element 2. So I write the code and I click on run. K2 also gets calculated and gets stored in the MATLAB memory. So this is my K matrix, the 2 by 2 matrix, 1.66 times 10 raised power 5 at position 1, 1, like that. So after we have defined our local stiffness matrix, the next step is to define the global stiffness matrix of the structural body. This is the fun part, and this is the interesting part. In assembling the global stiffness matrix by adding the local stiffness matrix to the how do we add the local stiffness matrix? How do we assemble the global stiffness matrix? There's a systematic process which I will show you on how to do this. The first thing you need to do when you're assembling the global stiffness matrix, the first thing you need to think of is what is the size of the global stiffness matrix of your question, of the question. Since in the finite element model, we're using as 3 nodes, node 1, node 2, node 3. So the size of our global matrix, our global stiffness matrix is going to be a 3 by 3 square matrix. So now, since if that is known, that the size of our global stiffness matrix is a 3 by 3 matrix, the first thing we need to do now is to create a base matrix. That base matrix is actually a zero matrix. We create a 3 by 3 zero matrix. And to do this on MATLAB, it's very easy using the zero inbuilt MATLAB function. Zero is an inbuilt function in MATLAB, which is used to create a zero square matrix. You specify the size of the zero matrix by entering the number here. Since I want a 3 by 3 matrix, I'll put 3 here. So my K is my global stiffness matrix. So I'll say K equals to 0, open bracket, close bracket, 3. So I write this code, I run. This 3 by 3 zero matrix gets generated. So after I've created this zero matrix, the next step is to add my local stiffness matrix to the zero matrix. I will add my K1 local stiffness matrix to the K matrix, and I'll also add the K2 local stiffness matrix to the zero matrix. So to do this, for the K1 represents the local stiffness matrix of element 1. And we know that element 1 is, this is element 1, and is between node 1 and node 2. So it means that this is the K1 matrix. The K1 matrix is a 2 by 2 matrix. I want to add it to this zero matrix. But where do you want to add it in the zero matrix? I want to add it at position between position 1 and 2 along the row and position 1 and 2 along the column. At this position, at this position, at this position, at this position. Because element 1 is located between node 1 and node 2. So I want to add my K1 in this position. So to do that, this is done using this simple MATLAB line of code. What this line of code actually means, what's in the bracket, 1 column 2 means from 1 along the row from 1 to 2 and along the column from 1 to 2, add K1. So you write this here equals to, you also write the same thing, plus K1. If you write this code and you run it, you see K1 gets added in this 4 position, at position 1, 1, 2, 1, 2, 2, and 1, 2 of the 0 K matrix. So I've added my K1 matrix to the 0 K matrix. The next step is to add the local stiffness matrix of element 2 to the 0 K matrix. And you do this the same way we did for K1. You should know that element 2 is between node 2 and node 3. So it means that we are going to add K2 between between 2 and 3 along the row. Let me show you. 2 and 3 along the row, and 2 and 3 along the column. That is at this point, at this point, at this point, and at this point. So we do this using this MATLAB code. So what's in this bracket means from 2 column 3 means from 2 to 3 along the row, comma, from 2 to 3 along the column, add K2 in that position. So you write this equals to this plus K2. Once you write this code, you write the code and you click on run, K2 gets added. This value here is our global stiffness matrix for the finite structural model. Now that we have defined the global stiffness matrix for the finite element model, the next step is to define the global force vector. And we should, because number of nodes Number of node is of our structure model is 3. That is node 1, node 2, node 3. The total number of node is 3. It means that the size of the force of our global force vector is going to be a 3 by 1 matrix. And since we only have 160 kilonewton force applied at node 3, and at node 1 and node 2 there is no force, it means that at 1 and 2, I define it as 0, and at 3 I define it as 160 Newton force, positive 160 Newton force. So this is how you write it on MATLAB. You open bracket 0 semicolon 0 semicolon 160,000 Newton. The unit I'm using for my force is Newton. I converted the 160 kilonewton to Newton. So that's why it's 160,000 Newton at position 3. So I write this code and I click on run. F gets generated too and gets stored in the MATLAB memory. So now I've defined the global force vector for our finite element model. The next step is for us to impose boundary condition to our global stiffness matrix and our global force vector. In order to apply boundary condition to our problem, we need to eliminate the rows and column where we have support degree of freedom. In our problem, in our finite element model problem, we have support degree of freedom at node 1. So we need to eliminate row 1 and column 1 in our global stiffness matrix, in our force vector, in our global force vector. So it means that, let me show you our global stiffness matrix. This is our final global stiffness matrix. We need to eliminate this column, and we also need to eliminate this row. Once the rows and column are eliminated, we will only have this remaining. So this is our modified global stiffness matrix, which I will denote in this my lesson as mod K. So I say mod K. I define mod K as our modified global stiffness matrix, and you do this. I will extract. I'm going to extract these values using this MATLAB code. So I'm extracting it using like K. I'm calling K open bracket. Extract the element between row 2 and 3 and column 2 and 3, and between extract the element between row 2 to 3 and the element along the column between column 2 and 3. So if we should run, I've written this code, if I should run it, I get this. So this gets stored in mod K in my MATLAB memory. So this is my modified global stiffness matrix. Now we need to modify our global force vector. The same way, we need to eliminate this first row. So we eliminate this first row, it only remain the element in row 2 and 3, that is 0 and 160,000 Newton. So you do this like this. For F, which is our global force vector, you open bracket between row 2 to 3, comma, column 1. So this MATLAB code extract the two elements between row 2 and 3, which is 0 and 160,000 Newton mod F. So now this is our modified global force vectors. Now that we have defined um, our modified stiffness, our modified global stiffness matrix, and our modified global force vector, mod K and mod F respectively, we can now calculate our displacement vector, our modified displacement vector, with the formula, the inverse of the mod K times the modified force vector. In MATLAB, there is a function called INV. It's an inbuilt MATLAB function which is used to find the inverse of a square matrix. So that's what I'm using to invert this mod K. So I'll say inverse of mod. I put mod K as an input variable in the inverse function. So putting this mod K in the function, I'm multiplying the results by mod F. I get my modified global displacement vector calculated, given as a 2x1 matrix, 1.44 and 2.4. What is the meaning of these two values? The 1.44 is the displacement quantity at node 2, and the 2.4 is the displacement quantity at node 3. If we want, because this is our modified global stiffness matrix. Remember, we've eliminated row 1. So the value here is for node 2 and node 3. So this is Q2, this is Q3. So we can form the global displacement vector Q. Since we know that Q1 is 0 because there's a support there, there's no movement there, you can open a square bracket, we put 0 here, half column, and mod Q, and we enter mod Q here, which is already calculated. If you do that and you run the code, you get your global displacement vector, your complete displacement vector from node 1, node 2, node 3. Node 1 is 0, node 2 is 1.4, node 3 is 2.4. So this is our displacement quantity at the node. I'm going to compare this result with the ARM calculation so that you appreciate and better understand the meaning of these values here. After we have determined our displacement vector, the next step is to determine the stresses in each of the elements. We have two elements in our problem, element 1 and 2. We use this general formula. In this formula, L is the length of each element, E is the Young modulus. And this Q1, Q2 is our displacement vector, a 2x1 displacement vector. And that is like for an element at the initial node, the Q1 is the displacement at the initial node, while Q2 is the displacement at the final node. So for element 1 in our own problem, Q1 is 0. Q1 is 0, Q2 is 1.44. For element 2 is between node 2 and node 3. So it's between node 2 and node 3. So our Q1 for element 2 is this 1.44, and the Q2 for element 2 is 2.44. We are going to see that when I'm calculating the stress in my MATLAB line of code. So I'm using this formula here to calculate the stress in each element. I denote the stress using this variable sigma 1. So sigma 1 equals to E1 times this minus 1 1 vector divided by the length, this L, multiplied by this displacement vector. Since element 1, the first position will be 0, Q1, and the second position will be the first element of the modified Q matrix, 1.4. This 1.4 is the displacement at node 2. So I'm extracting 1.44 from mod Q using this. So I've written this code, but I should run it. I get my stress in element 1, sigma 1, to be equals to 3,200 megapascal or 3,200 Newton per meter square. The same thing is done for the second element to calculate the normal stress. E2 times this matrix divided by L2 times mod Q. Here I'm not using a bracket because mod Q is actually my displacement vector which I need. I don't need to modify it. In mod Q, this is my Q2 and this is my Q1. 1.4 is my Q1. 2.4 is my Q2. So I just insert the vector here, and when I run the code, I get my normal stress to be equals to 1,600 megapascal or 1,600 Newton per millimeter square. Comparing the stress value of this finite element procedure with the manual calculation, we see that the normal stress in element 1 is 3,200 and the normal stress in element 2 is 1,600. In PowerPoint calculation, we see the normal stress in element 1 is 3,200 megapascal, in element 2 is 1,600 megapascal. The extension in element 1 is 1.44. Actually, it's 1.44, while the extension in element 2 is 0.96. This 1.44 is, in using my finite element calculation, is actually Q, as in the Q value here minus the Q value here. It is in my finite element calculation, we saw that our Q2 value here is 1.44 and our Q1 value here is 0. So 1.44 minus 0 gives 1.44. And also for element 2, we found that the extension in the member is 0.96. And this 0.96 is gotten from the Q value in node 3 minus the Q value in node 2. And we know that our Q value at node 3 from our finite element calculation is 2.4, and our Q2 value is 1.44. So if we subtract 2.4 from 1.44, we'll get 0.96. I'm going to show you this on MATLAB now. So you can see that our Q3 is 2.4, our Q2 is 1.44. So we want to get the extension in element 2, say DL2 equals to Q3 minus Q2. If I should run it, you can see I got 0.96. This is the extension in element 2. So we can see that the result of finite element procedure is exactly the same with hand calculation using two finite linear elements. So this is the procedure of how to use finite element method for solving one-dimensional problem by elimination method. In my next video, I'm going to use the penalty approach to solve this same problem. When when I'm uploading this video on YouTube, I'm going to also upload a link where you can download a textbook where you can read on your own. You can where you can read on your own on the topic of finite element and procedure for solving structural engineering problems. Now I've come to the end of this lesson. I am very grateful and I thank you so much for watching my video on YouTube. Next video will be uploaded in 2, 3 or 4 days time. Thank you so much. Bye bye.